Okay, let's continue. Theorem 4. In triangle ABC, DA is on BC, DE is in parallel with BA, meets AC on E, which can be drawn like this. Right? We have triangle ABC here. D is a point on the BC, and we know that D is in parallel with AB and meets AC on E. DF is in parallel with CA and meets AB on F. AD is a conjugate median of triangle ABC if and only if B, C, E, F are cyclic. So we can assume that if B, C, E, F are cyclic, right? If B, C, E, F are cyclic, and we want to prove that AD is a median, is a conjugate median, which means that we want to prove that BD to DC equals to AB to AC squared, right? So what is BD to DC? BD to DC equals to BF to AF. Right? BD to DC equals to BF to AF, and it equals to BF to FD times FD to AF. Right? Why do I want to bring the BF to FD here? Because the BF to FD equals to AB to AC. Right? So it equals to AB to AC times FD to AF. And what is FD to AF? Because AF is in parallel with DE, FD is in parallel with AE, that means AFDE is a parallelogram, which means FD to AF equals to AE to AF. So it equals to AB to AC times AE to AF. Now we think about the problem set that BCEF are cyclic, which means AF times AB equals to AE times AC, right? That means AE to AF equals to AB to AC. So here we got AB to AC squared. That's the case if BCEF are cyclic. So if BD to DC equals to AB to AC squared, can we prove that BCEF are cyclic? BD to DC equals to AB to AC times AB to AC. And AB to AC equals to BF to FD times AB to AC, right? And BD to DC also equals to BF to AF, so which means BF to FD times AB to AC equals to BF to AF, which means AB to AC equals to FD to AF, right? FD to AF equals to AE to AF, which means AB times AF equals to AE times AC, which means BCEF are cyclic. Okay, that's theorem 4. And we have the conclusion 5 here, which is saying that in a right triangle, the projection points from the foot of altitude on hypotenuse to the two right sides and vertices of hypotenuse are cyclic. It's actually saying that if we have a right triangle here, and we find this is a right triangle, we find the altitude on the hypotenuse and then we find the foot of this altitude, and then we do the projection from this foot to the two other right side, right? Then we know that because this is 90 degrees, so this actually in parallel with this, and this one is in parallel with this one. So if AD is a conjugate median, then we can say that BCFE are cyclic, right, based on what we just proved. And how can we prove that AD is a conjugate median? We just need to prove that in this right triangle, BD to DC equals to AB to AC squared, right? And BD to DC equals to BD to AD times AD to DC. And we know that BD to AD equals to AB to AC, AD to DC, AD to DC equals to AB to AC. So this equals to AB to AC squared. Okay, let's learn about the theorem 5. In acute triangle ABC, D is on edge BC, circle O1 passes through AB and tangent to AC on A. So this is saying that we find the acute triangle first. Okay, A, B, C here. And we already know that circle O1 passes through AB and tangent to AC. That means O1A is perpendicular to AC, right? So we can just find the perpendicular line of the AC that passing through A, and we find the intersection point of this line and the perpendicular bisector of segment AB. Then we know this would be the center of this circle, right? And similarly, we can get the same angle here, right? Because this O2 passes through AC and tangent to AB on A. So it's a similar case. It's O2 here. AQ is a common chord of circle O1 and circle O2. So let me just draw this. Right, that's the circle O1, and roughly say it's about here, right? So that's circle O2, okay? And this is AQ. AQ is a common chord of circle O1 and circle O2. AD is a conjugate median if and only if AQD are collinear. Basically, we just need to prove that AQ is a conjugate median of the triangle ABC, right? We just need to prove that. Okay, I think we should be already familiar with proof of the conjugate median, right? Because we want to prove that BD to DC, we just need to prove that BD to DC equals to AB to AC squared. We basically just need to prove that sine angle BAQ to sine angle CAQ equals to AB to AC, right? Using the area of the triangle, we can easily get this one. So we want to prove this, to prove that AQ is a conjugate median. And look at here, we want to prove the relationship between sine angle BAQ and sine angle CAQ. We need to know what is this angle, right? And the problem set only tells us that O1A is perpendicular to AC and AB is perpendicular to AO2. So if we connect O1, O2, if we connect O1, O2, then we know that AQ is perpendicular with O1, O2, right? So we know that angle BAQ plus angle QAO2 equals to 90 degrees. And we know that angle QAO2 plus angle AO2O1 equals to 90 degrees. This means that angle BAQ equals to angle AO2O1. And similarly, we can get angle CAQ plus angle QAO1 equals to 90 degrees, and angle QAO1 plus angle AO1O2 equals to 90 degrees, which means angle CAQ equals to angle AO1O2, right? Now sine angle BAQ to sine angle CAQ equals to sine angle AO2O1 to sine angle AO1O2, right? So sine angle BAQ to sine angle CAQ equals to sine angle AO1O2 to sine angle AO2O1 to sine angle AO1O2, right? Sine angle AO2O1, sine angle AO2O1, sine this angle, that is half of AQ to AO2, right? Half of AQ to AO2. And to the sine angle AO1O2, sine angle AO1O2, which is half of AQ to AO1, which equals to AO1 to AO2, right? It equals to AO1 to AO2. And notice that this angle equals to this angle equals to this one equals to this one, which means angle AO1B equals to angle AO2C, which means 2R sine angle AO1 to R1 sine angle AO1B equals to AB, and 2R2 sine angle AO2C equals to AC. These two are equal, which means R1 to R2 equals to AB to AC. What is R1? What is R2? R1 to R2 equals to AB to AC. That means AO1, that's R1, right? AO2 is R2, so it equals to AB to AC. So we just prove that this is valid, which means AQ is a conjugate median of the triangle ABC. Okay. That's for theorem 5. And let's look at the conclusion 6. Conclusion 6 is saying that in the triangle ABC, D is on the side BC, and Q is on the segment AD. AD is a conjugate median of triangle ABC if and only if angle BQ equals to angle AQC. Angle BQA equals to angle AQC. And the triangle ABQ is similar to triangle CAQ. Right, triangle ABQ is similar to triangle CAQ. And this angle equals to this angle. That means the angle BAQ, this one, the angle BAQ equals to angle QCA, right? Or we can see it here, BAQ equals to angle ACQ, right? And we know that we can find the we can just find this O1, O2 by the similar way, and we know that angle ACQ equals to angle AO2, O1. Similarly, we can demonstrate that angle CAQ equals to angle AO1, O2. Right? And we just know that if this is true, then we can get sine angle BAQ to sine angle CAQ equals to AB to AC, which means AQ is a conjugate median. Okay? That's a problem. That's a conclusion 6. Now let's look at theorem 6. Theorem 6 is kind of complex if we draw the figure manually. So I print it out. Let's read the problem and look at the figure, and then we think how to address it. Okay, in the triangle ABCD is on side BC, so neglect this sentence for now. Find EF on AB and AC respectively, so that EF is in parallel with BC and BF meets CE on P, right? So we find the EF is in parallel with BC, and we connect BF and CE, that's intersection point P. Let M be the Minkow's point of the complete quadrilateral AEBPCF. So that's why I said if you are not familiar with the Minkow's point, please reference to the previous video talking about the Minkow's point, so you have the idea how to get it and what it is. So here I just briefly introduce it. It's saying that in a complete quadrilateral, we can always find a point, right? Such that the circumcircle of the triangle BEP, triangle BAF, triangle CPF, triangle CEA are concurrent on one point, and that point is called Minkow's point, which here I mark it as M. Okay. So M is a Minkow's point of the complete quadrilateral AEBPCF. Here we have AEBPCF, right? M is Minkow's point. Then AD is a conjugate median of triangle ABC if and only if ADM are collinear. Basically, it's just asking us to prove that AM is a conjugate median of the triangle BAC, right? Okay, so since now you're already familiar with proof method, so we just skip some of them. We just need to prove that sine angle BAM to sine angle CAM equals to AB to AC, right? Similar idea, just extend this here, and we know that BD to, we call it D, but you can call it D prime. So BD prime to DC prime equals to the area of triangle BAD prime to the area of triangle AD prime C, and then you can use the area formula, and then you can get one AB to AC. So we just need to prove the rest part, which is a sine angle BAM to sine angle CAM. We want to prove it equals to AB to AC. Okay, so what is sine angle BAM? What is angle BAM? The angle BAM equals to, because EACM are cyclic, so angle BAM, that is angle EAM, right? And it equals to angle ECM. And because PMCF are cyclic, again, based on the Minkow's point property, right? Because P, M, C, F are cyclic, that means angle ECM, which is angle PCM, equals to angle PFM. Okay, so if I mark it, we got this angle, right? That's the angle BAM equals to this angle ECM, and equals to this angle PFM. And also for the angle CAM, for the angle CAM, it equals to the angle CEM, right? And because angle CEM is angle PEM, and because BEPM are cyclic, so it equals to angle PB, it equals to angle PBM, right? So this angle equals to this one, equals to PBM, which is this one. Okay. Now if we think about the angle MFC, right? Remember we want to find the ratio of the sine angle BAM to sine angle CAM, right? Sine angle BAM to sine angle CAM, which is sine angle PFM to sine angle PBM, right? So sine angle BAM to sine angle CAM equals to sine angle PFM to sine angle PBM, which equals to PFM to PBM, that is MF to BM. PFM to PBM, right? So BM to MF, that's the correct one. Okay, now we want to prove, basically we want to prove that BM to MF equals to AB to AC. We want to prove that. Okay, so we want to find the relation between BM and MF. Now if we look at the triangle MFC and triangle MBE, right? Because AFMB are cyclic, so angle MFC equals to angle ABM, which is angle EBM, right? Angle MFC equals to angle EBM. And because AEMC are cyclic, that means angle BEM equals to angle FCM. Okay, that means in the triangle MFC and triangle BEM, we have this angle equals to this angle and this angle equals to this angle. These two triangles are similar, right? These two triangles are similar, then we can get BM to MF equals to BM to MF equals to BE to FC, right? Equals to BE to FC. And because EF is in parallel with BC, so BE to FC equals to AB to AC. Okay, then we just get it. We get that sine angle BAM to sine angle CAM equals to AB to AC. Then AM is a conjugate median of the triangle ABC. Okay. And that's theorem 6. And based on that, we have the conclusion here. That conclusion 7, in the triangle ABC, EF are on ABAC respectively. BF meets CE on P. That's the same as what we have in the figure. BF meets CE on P. M is a Minkow's point of complete quadrilateral AEBPCF. That's the same here. The only difference is that line AP meets the circumcircle of triangle ABF on N. So line AP meets the circumcircle of the triangle ABF, which is this circle on point N. Okay. And the same line meets the circle AEC on L. AEC, let's say circle on L, right? AP meets it on L. Then it's saying that AM on the line of the conjugate median of the triangle ABC if and only if one of the following conditions. First one, EF is in parallel with BC. Second one, NM is in parallel with BF. Third one, LM is in parallel with EC. So if you look at the figure, we just prove that if EF is in parallel with BC, then AM is a conjugate median, right? And we want to prove that NM, if NM is in parallel with BF, or ML is in parallel with CE, then AM is also the conjugate median of the triangle ABC. Basically, we just need to prove that if NM is in parallel with BF, then we can prove that EF is in parallel with BC. Then we're done, right? So that is saying we just need to prove that EF is in parallel with BC if and only if NM is in parallel with BF or ML is in parallel with CE. And if you look at the symmetrical of this left side and the right side, that's basically we just need to prove one condition and the other one is obvious, right? So let's try to prove if EF is in parallel with BC if and only if NM is in parallel with BF. Okay, in whichever it's fine because it's problem like this kind of like every step are reversible, which means that we can always trace back to prove another condition. So let's just assume that EF is in parallel with BC, which we're already familiar with. So let's assume that EF is in parallel with BC. Now we want to prove that NM is in parallel with BF. Right? We want to prove that NM is in parallel with BF. Okay, think about this. If we want to prove that NM is in parallel with BF, and we already know that A, B, M, F, and N, these 5 points are cyclic, right? Which means this is a parallel line on a circle. That is saying we just need to prove that MF equals to BN. We proved that MN is in parallel with BF, right? We just need to prove MF equals to BN. And because they are on the same circle, so we don't really need to prove the length of the chord. Instead, we can just prove the circular angle reference to this chord, which means we want to prove that MF, so this one is equivalent to MF equals to BN, which is equivalent to angle MAF equals to angle BAN. Right, we just need to prove that angle BAN, which is angle EAP, equals to angle MAF, which is the angle MAC. Why I want to say the angle MAF equals to MAC and angle, why I want to demonstrate this as this way, that angle BAN, I call it angle EAP. Just because I noticed that angle AMC equals to angle AEP, right? Because AEMC are cyclic. So if this is valid, that means the triangle AEP and triangle AMC are similar, which means that we can just prove that triangle AEP and triangle AMC are similar with using the condition we already know that angle AEP equals to angle AMC. Then we can prove that angle MAC equals to angle EAP, right? So it equals to prove that triangle AEP is similar to triangle AMC, right? And we already know that angle AEP equals to angle AMC, which means that we just need to prove the equivalent to prove that AE to EP equals to AM to MC, right? It equals to proving this one. And let's just look at the segment here. AE and EP and AM and MC, right? So for the triangle PMC, it has a MC, this part, right? Because it's difficult to directly prove this one, so we have to use other similar triangles to prove it. Then if we look at here, the triangle PM, well, the triangle, of course, we can easily recognize that triangle EMC is similar to triangle BMF, right? But that's not really helpful. So for here, let's think about the triangle PMC, right? Because this angle, the angle MCP equals to angle BAM, right? Angle MCP, this angle equals to angle BAM, this angle. And also, the angle MPC equals to angle MFC, right? Angle MPC equals to angle MFC, and angle MFC equals to angle MBA, right? Because AF and B are cyclic. So this angle equals to the angle MBA. So I just mark it here, this one we're talking about, right? That means triangle PMC is similar to triangle ABM, right? Triangle PMC is similar to triangle, let me be careful, PMC BMA, right? And based on this, we can get that AB to PC, right? AB to PC equals to PM to BM equals to MC to MA, right? And remember that we want to find a way, use AEEP, AEEP, and AMMC. Now we actually have the AM and MC here. right? So we just need to prove that AE to EP equals to one of these, right? AE to EP equals to AB to PC. Can we prove that AE to EP equals to AB to PC? Can we prove that? This is obvious, right? Because AE to AB equals to EF to BC, which equals to EP to PC. So we find that AE to EP equals to AB to PC equals to MC to MA, which is here AM to MC, which means that the triangle AEP and the triangle AMC are similar, which means the angle MAC equals to angle EAP, which means the angle MAF equals to angle BAN, which means MF equals to BN, which means NM is in parallel with BF. Okay, so basically, this condition, the EF is in parallel with BC, helps us to get this done, right? To get this done, and then we can go back to prove that NM is in parallel with BF. Similarly, we can just prove that ML is in parallel with CE. Okay, so it demonstrates that conclusion 7 is correct, which means that either EF in parallel with BC or MN is in parallel with BF or ML is in parallel with CE. We can have the conclusion that AM is a conjugate median. Okay, that's basically the concept and theorems properties of the conjugate median. I think this is very interesting topic, and I believe it's been researched for 1,000 years, and still people are working on this one and trying to dig more properties of the conjugate median. So here it's just the most basic and the foundation of it. I hope you like this video. See you in next one. Thank you.